Okay, so in this lesson, here's our screencast walkthrough of 2.2 position and velocity graphs. So some announcements real quick. Please turn in any missing work, classwork 0.1, classwork 2.1, along with any labs to receive full credit. Okay, or better said, not full credit, but have no late penalty. Okay, and then Unit 2, Quiz 2, motion graphs is on Monday, 10/12. Okay, so our agenda for today is to go over motion graphs activity, motion graphs discussion. Wednesday, Thursday, we'll look at motion graphs notes and motion graphs learning activities. Since this is a screencast, the motion graph activity and discussion, along with some of the learning activities, will not be accounted for as this lesson is, as the screencast is meant to capture just the main points of the lesson. So we'll skip over motion graphs activities. So we get to position versus time graphs, okay? So position versus time graph, the idea is that time is graphed on your x-axis, whereas position is graphed on your horizontal axis, or excuse me, vertical axis, your y-axis. So going to the right or heading upwards is increasing on your position axis, while heading to the left or heading downwards is marked by decreasing, heading downwards on your position axis, okay? So the essential characteristics of a position versus time graph are that a constant velocity consists of constant steepness. Speeding up, graph becomes more steep, and slowing down, the graph becomes less steep. When you change direction, the direction of the graph switches, aka you're going to have a hill or valley. Okay, so let's take a look at some of these things in a little bit more detail. Okay, so right here for the first part of our position versus time graph, we have a relatively constant speed or constant velocity because we have a constant steepness. So steepness is equal to speed on a position versus time graph. Okay. So we're going to speed up, so we're going to have a constant velocity, we're heading to the right, or heading upwards, I guess if we're jumping, okay? And then as we start approaching right here, we're going to be slowing down because our graph is becoming less and less steep. And then right here, at this time, we change direction, we have a hill, specifically we're changing from the right to the left because now we're heading downwards. And now we're speeding up because our graph is going to become less and less steep, or excuse me, it's going to become more and more steep, okay? So a change in direction always has a hill, is accompanied by slowing down and speeding up, just in the same way that if you make a U-turn, you're going to slow down to make the U-turn and then speed up afterwards. So now we move on to velocity versus time graphs. On a velocity versus time graph, the main difference is that velocity, instead of being graphed as the steepness of a slope or of a position versus time graph, velocity itself is actually now on the vertical axis, okay? So the essential characteristics now of velocity versus time graph is that you'll have a constant velocity if your graph remains flat and horizontal. The idea being is that if your graph is flat and horizontal like this line I'm making right here, that's indicating that's staying at a constant velocity, okay? Speeding up means your velocity is going to head away from the 0 meters per second mark, which is represented by the time axis. The idea being it's like a speedometer in a car. If you speed up in a car, the speedometer dial is going to move away from 0 meters per second or 0 miles per hour. And then slowing down, the velocity is going to head towards 0 meters per second because like in a car, if you brake in a car, the dial of your speedometer heads towards 0 meters per second or 0 miles per hour. Okay? And then your changing direction happens when your graph crosses the time axis, whether from positive to negative or negative to positive, because velocity tells us, the sign of our velocity tells us which direction we're heading. So if our velocity changes signs, that means we're changing direction, okay? So if we look at this graph right here, we can see that we're heading in the positive direction, okay, at first, because our graph is in the positive section of our velocity axis, okay? And then now we're starting to slow down because our graph is heading towards 0. It's heading towards this time axis. All right, and then at this spot right here, we change direction because our velocity is changing from positive to negative, okay? And then after this time, we are starting to speed up again because now our graph is heading away from 0. It's heading away from the time axis. So we can do a problem here together to explore what's happening, okay? There we go. So right is a velocity versus time graph for a car that is being studied in a wind tunnel. Okay? A asks at what times is the object speeding up in the positive direction? Okay? So there are two things we need to focus on here. Better said, actually three things. Okay? The first one is we need to determine if we're looking at a velocity versus time graph or a position versus time graph. Because a velocity versus time graph is going to have different features and characteristics from a position versus time graph. Okay? So what we can see here is we're looking at velocity versus time graph, so we need to think about the characteristics of a velocity versus time graph here, okay? So for A, at what times is the object speeding up in the positive direction, okay? So there are two criteria we need to think about. What does it look like? What does a graph look like if an object's heading in a positive direction for a velocity versus time graph? And what does a velocity versus time graph look like when object's speeding up? So let's think about the positive direction first, okay? So in a positive direction on the velocity versus time graph, that means our graph is going to be in the positive velocities. So we see our graph is in the positive velocities from 0 to 30 minutes, okay? So now we constrict our attention to 0 to 30 minutes, and now we have to think about, okay, within this 0 to 30 minute time frame, okay, when are we speeding up? And again, this is where we now need to think about the conditions for speeding up on a velocity versus time graph. All right, speeding up in this case for velocity versus time graph is going to be denoted by moving away from the time axis or the 0 meters per minute mark. So we can see we're speeding up from 0 to 10 because our graph here is moving away from this 0 meters per second mark, this time axis. So the car is speeding up from 0 to 10 meters as the velocity is positive and heading away from 0 over this time interval. Next, we ask at what times does the object change direction? Okay, so it might be tempting in this case to say 15 minutes, or it might be tempting to say 40 minutes because we see we have a hill and a valley right here. However, that would be if we're thinking about a position versus time graph. Here we are looking at a velocity versus time graph, so we need to think about the criteria for changing direction of velocity versus time graph. Specifically that our graph crosses the time axis and changes signs. So that tells us that our car is going to change direction at t equals 30 minutes because we see our velocity change direction from positive to negative, or change sign, excuse me, from positive to negative, okay? We can't say that we're changing direction at 0 minutes or at 55 minutes because even though we get close to crossing the time axis, we never actually cross. So we can't say for sure whether we change direction at 0 minutes or 55 minutes. Motion graphs matching activity we can't do. This is an in-person activity, okay? So we have a check for understanding. We're going to sketch a velocity versus time graph for an object that does the following. Heading to the left and slowing down, turns around to 5 seconds, and begins to speed up to the right. So you can pause the video at this time and do this on your own, or we can walk through this together. So here's what our graph is going to look like, okay? Our graph is going to look like this right here. The idea being is first we need to sketch a graph that's heading to the left, which means we need our velocity versus time graph to start off in the negative part of our velocity axis. Next, we're going to take note of that we're going to be slowing down. So we're going to start off in the negative section of our velocity axis, but we're going to be heading towards the time axis, aka where that 0 meters per second is. At 5 seconds, we're going to change direction, so our velocity is going to change signs from negative to positive. Okay, and then we're going to speed up to the right. So now we're at positive velocity, which means we're heading to the right, and now we're going to speed up, which means we're going to head away from the 0 meter per second mark, away from this time axis. So this is what your velocity versus time graph would look like in this specific case. So interpreting motion graphs, okay? So the interpreting motion graphs activity right here, all right, is going to be done as a classwork. Okay, so I'll give you some samples of what an interpreting motion graph activity should look like for your classwork for today, okay? So you can look up the classwork 2.2 in the Google Drive folder for reference, okay? So the idea is you're going to sketch a position versus time graph that contains speeding up, slowing down, and then a change in direction, okay? Like we see happening from C to D. We change direction from C to D, okay? Then you're going to write a story describing what's happening to motion or object over entire position versus time graph. So example right here would be Mr. Heffley starts 25 meters to the right of his house. He speeds up at point B because we see our position versus time graph get steeper, and then slows down at point C because we see our position versus time graph get much less steep. From C to D, Mr. Heffley is at rest 5 meters from his house. At D, he begins to speed up and move away from his house. Okay? So this is a real cut and dry example. You can get much more creative with this. In fact, you must meet a length requirement of 1 paragraph at least for your story, and each paragraph must be at least 5 sentences in length. Okay? And then you're going to repeat the same procedure, except you're going to come up with a unique new graph that's a velocity versus time graph that contains, again, the features of speeding up, constant velocity, slowing down and changing direction. Okay, but this time you have to come up with a unique new story. So you're going to have two graphs and two unique stories. Okay, so for example, for this velocity versus time graph, I could say Cosmo starts at rest and begins to speed up to the right over section 1 because he really needs to use the bathroom. Okay, over section 2, he decides he doesn't need to go so bad. He continues to move at the right at a constant velocity. Okay, we see we have a constant positive velocity right here, so we can see we're heading to the right. All of a sudden, over section 3, he feels a sharp pang of regret of having drank 12 Mountain Dews and begins to speed up again. Over section 4, he begins to slow down as he sees a heralded porcelain throne, so we see we're slowing down because we're heading towards the 0 here. And then after 20 seconds, t equals 20 seconds in section 4, he turns around and speeds up. Lastly, at section 5, he comes to move at a constant leftward velocity. So this is what you're going to be doing basically for your activity, and you can reference Classwork 2.2 for more specific guidelines. All right, so quick check for understanding then to wrap up this lesson. Okay, which graphs represent an object that is speeding up? Okay, so we need to be careful with this question right here, because if we look, not all graphs are the same. Yes, they have different shapes. We can also see some graphs are position versus time graphs, whereas graphs 3 through 5 are velocity versus time graphs. So for 1 through 2, we need to look for, we need to think about what characteristics are shown for an object that's speeding up on position versus time graph, okay? Well, in that case, a position versus time graph, okay? For this case, a position versus time graph will get steeper and steeper and steeper as we speed up. So we can see actually that graph number 2 shows us speeding up because we can get steeper, steeper, steeper as time goes on. However, there's a possibility that we can have more than one option that's correct here because we can see C and D both contain multiple options. So if we go to a velocity versus time graph, we now need to think about what does it mean for an object to speed up on a velocity versus time graph. What does that look like? Well, if we recall, on a velocity versus time graph for speeding up, it means we're going to be moving away from our 0 or time axis. So if we look at our graphs, we can see that 3 doesn't show this. 3 shows a constant velocity. 5 doesn't show this because 5 shows slowing down. We head back towards the 0. But 4 does show speeding up, specifically speeding up to the left because our velocity is heading toward or away from the 0 meter per second mark. So both 2 and 4 show us speeding up. And this is our lesson for position and velocity graphs.